Now we move on to testing and errors. So first we state the null and alternative hypothesis. Then we decide whether we have a right-tailed, left-tailed, or two-tailed test. And then the testing and possible errors. Once the hypotheses are stated, the researcher, and in that case that'll be us, designs the study. The researcher then selects the correct statistical test, which we'll get into more detail later, and chooses a level of significance. I believe I chose to do errors in a separate section, so we'll just say this section is on testing. Okay, back in example 1, the researcher might select various viewing hours for the network and record the length of time the commercial take in that programming hour. So maybe we'll take some hours from prime time, maybe we'll take some hours from daytime, from morning, make sure we include weekends and weekdays, and among all those various programming hours, we would go ahead and record the length of time that commercials take up in a single hour. Now the average length of time of commercials per viewing hour, so we take all those hours, average them together, it might not be 14 minutes exactly. Very possible that that would happen. If the mean length of the commercials per viewing hour is 14.1 minutes, the researcher might say, oh, that difference is not that bad, or maybe it's just due to chance, meaning the natural variation in hour to hour. And we would not reject the null hypothesis. We would say that, yeah, commercials really are about 14 minutes long in a programming hour. But if the mean length of commercial hours is 14.9 minutes, the researcher might conclude that viewers are correct and they would reject the null hypothesis. Maybe that number is large enough to say, oh, I think we're a little bit more than 14 minutes. And so we would reject the null hypothesis that says commercials are 14 minutes average and say that, yeah, they're a little bit longer. But the problem comes in with this. Is 14.1 minutes close enough to say that it's 14? What about 14.4? Is 14.8 too far away? We don't know. This is where that's when our test will tell us. The question becomes, where do we draw the line? Where's the line between being close enough to 14 minutes to say, yeah, it's about 14 minutes, or too far away to say that it's approximately 14 minutes. Once we calculate the appropriate test value or test statistics, which we'll talk about later with specific testing methods, we compare that to a critical value to make the decision. So what we're saying is the value too far away to be considered around the same value that we're talking about? So that brings us to critical values, critical regions, and significance level. So just like with the programming, we would take these samples. And if we remember back to the central limit theorem, it says that the distribution of the means of the samples will become approximately normal regardless of the distribution of the original data. So I might take samples more than once and take those means, and those means will eventually follow a bell-shaped curve. So because we're taking samples to compare to our population value, we're always going to be looking at a bell-shaped curve. Now, part of the area under the curve will represent values that are not too far away from the value we've stated in the null hypothesis, but values that are too far away and thus statistically different will fall in what's called the rejection region. Values in these regions will cause us to reject the null hypothesis in favor of the alternative hypothesis. And these areas are usually going to be in one or both tails, depending on what type of test you're doing. The value that separates the critical region, the tails, from the non-critical regions, the middle part, where we will not reject the null hypothesis, is the critical value. So wherever we draw that line between being too far away and close enough, that value is called the critical value. And then we have the significance level alpha, which is the probability that the test statistics will fall out in that critical region, that tail. And again, just be careful. Make sure you have made the decision of whether you're doing a one-tailed or two-tailed test, whether it's right or left or two-tailed test. So let me give you a visual real fast of what's going on. So we have a bell-shaped curve, which we are used to from our standard normal table. And what we're saying here is if a value falls in the middle here, this is non-rejection region. And how wide that area is depends on the significance level. But if I have something that falls out here or out here, then that is the rejection region. And it depends on what this value is, a z-score, and whether or not something falls out there. And again, we'll get to specific values when we get to each specific test. Okay, let's take a look. Let's practice finding those critical values, which you've done this already with standard normal tables, but just tie it in connection with hypothesis testing. So example 4, use a standard normal table to determine the critical region and critical value based on the alternative H sub 1 where mu is greater than 14 and a significance level of alpha equal to 0.1. Now the 14 is coming from our commercial example. The commercials, are they longer than 14? We don't know. So what I'm doing here is I have a normal curve, bell-shaped curve that we're used to. And what I'm saying, and this is a right-tail test, which we determined before since we are greater than. So what I'm saying is this area here is equal to 10%. And that is the rejection region. Whereas over here, anything in this area, I do not reject. So what I'm trying to find is what is this number right here. Well, in your table, you're going to look until you find 0.1, or if you choose to use your calculator, you could use inverse normal. And looking on my table, and I don't have one here in the video, but looking on my table, the closest I get to 0.1 is 0.1003. That's pretty close. And that gives me a z-score of 1.28. Now, if you were looking on your table, you probably had to look on the negative z-score, but knowing that this is a right-tailed test and knowing that a normal curve is symmetric, go ahead and make that positive 1.28 because you're in the right tail. So the critical value would be 1.28. So if we had a test statistic that was larger than 1.28, that means it would fall in the rejection region and we would reject the null hypothesis. But if we had something smaller than the critical value, maybe we got 1.15, then we would not reject the null hypothesis. Okay, let's take a look at example 5. Similar thing here. This time we have that the alternative says mu is not equal to 20. So this is going to be a two-tailed test because we don't have an indication of being bigger or less than, just different, just not equal to. So this time in our picture, the total area in the tails is 0.02, this alpha here, but that means individually the tails are 0.01. But if I were to add those together, I'd get my 0.02. So again, I look on my table and I'm looking for an area of 0.01. And the closest I get to is 0.0102 and 0.0099. I think I'm going to take that 0.099. It's just a little bit closer. So that gives me a z-score of 2.33. So my critical values, I have two of them this time, since I'm two-tailed, is negative 2.33 and positive 2.33. So if my value, my test statistic, which we'll learn how to do later, if it were larger than 2.33 or smaller than negative 2.33, if it fell in either of those tails, then I would reject my null hypothesis in favor of the alternative. And finally, let's take a look at example 6. This time we have that mu is less than $80. I don't know the context of the problem that this may have come from, but we have a less than symbol. So that means this is going to be a left tail test. So in our picture, that means our tail here is 0.005. So I'm looking for the z-score right here. That would give me a tail of 0.005. So I'm looking on my chart. And if you notice, you have 0.0051 and 0.0049. And I believe our table makes the distinction of going halfway in between. And so they have a value of 2.575, or you might have gotten that on your calculator. If you use 2.57 or 2.58, I don't think that would be the end of the world. Usually it's better to go up a little, but 2.575, and this is going to be negative because we are in the left tail. So my critical value this time, and if we round it to 2 decimal places, would be negative 2.58. So this is stuff you've been doing before with all the normal table stuff. We're just connecting it with the concept of the alternative hypothesis from hypothesis testing.